theory and for this particular problem, I'll be focusing on work done by Reinhard Genzel and Hess, and the citation reads that they were awarded the Nobel Prize for the discovery of supermassive compact object at the center of our galaxy. Now, if you look at the document, like what they did was they studied the motion of different stars along the supermassive compact object and essentially detected that there is a compact object located at the center. So to sort of simplify this problem so that we can do this over the span of the next 30 minutes, what we'll do is we'll take some synthetic data, which is an observation which looks more or less like this, which is just position of the star at different instants of time. And the goal would be to find the location of this supermassive object. Right? So for a simplified problem, what we'll do is we'll consider these data points, and for an extremely simplistic analysis, we'll say that, okay, this is just a gravitationally bound system and it's a Keplerian model, and so the gravitational object lies in one of the foci, or the sun lies on one of the foci, and the goal is to find the location of the focus of this ellipse. We model this as an ellipse. So this is just to make it easier to understand and implement, rather than just talking abstractly in terms of different kinds of terminology. So what we have is the data, which is x and y. So x and y is, you can think of it as just the coordinates in space, which is the x and the y coordinate. Let us assume that the orbit is directly facing us, like there is no inclination angle, for the sake of simplicity. Obviously, when you apply it on real data, there are a lot more complexities, but we're just reducing it to the bare minimum for the sake of compactness. And the data would be of this form. If you can see here, like the blue dots and the red dots probably denote observations using different satellites or something like that, or observatories. And what we would be interested is to construct a model which would essentially be the orbit of the motion of the star around this compact object. So if you want to construct the model of an ellipse, you need the location of the foci, either of the foci, and the length of the semi-major and the semi-minor axis. So how do you go about it? Like suppose you're just given the data. How do you try fitting it? Like you would probably be familiar with least square fitting and all such. So through this, I would like to introduce a Bayesian parameter estimation. And what that is it's a parameter estimation which is based on Bayes' theorem, which is a theorem of conditional probabilities. So this, as you're all familiar with this, it says that the probability of A given B, the conditional probability of the A given B, can be written in terms of the conditional probability of B given A and the probability of A. And similarly, if we can apply the Bayes' theorem to the observed data, so what it happens is the probability of the parameters given the data is proportional to the probability of the data given the parameters and the probability of the parameters. So in essence, what this is that you start off with some prior information of your data. Say, in this case, you're looking at an ellipse. So we know that the prior information, we can definitely say that the semi-major and the semi-minor axes are within the bounds of this. So you already have some prior information of what the resultant quantities or the resultant model parameters are. That is R1 and R2. And we also know that one of the focus should lie on the bottom half of this ellipse. So you also have some information as to what the parameter values of Cx and Cy are, which is the x and y coordinate of the focus. So using this prior information, and you also have the additional data points, all the x and y coordinates, what you'd like to do is update your knowledge to improve upon the estimate of this. So what happens is you take the prior information, and this is essentially an application of Bayes' theorem onto the space of data, so to say. And this likelihood function essentially quantifies how close a model is with respect to the data. And using this, we'll be able to obtain what the posterior probability is, which is given a data, what is the most likely model, or what are the most likely model parameters. To explain each of these terms in more detail, a prior probability is essentially all the prior information which is available. So suppose you already have some other observation, and you have some additional observation which is adding to the data. Then you can use the previous observation as some sort of a prior on which you'll be improving on. It's like instead of constraining your model with one observation, it's like you're using both the observations to constrain your model. So that is like a prior. It's called the prior information. And for instance, the previous observation of say a semi-major axis R1 was 10 plus or minus 2 in some units. Your prior probability would be something like a Gaussian in the R space, where it's centered at 10 and it has a width of 0.2. Or if I told you that there is no prior information available, then what you would do is you come up with something known as an unbiased estimator, or a flat prior, which says that, okay, I know reasonably well there is a physical bound that the semi-major axis is some value between 6 and 14, and I don't give any bias, and I say all of them are equally likely, equally possible, because I have no prior information about it. So this is this particular quantity, the prior probability distribution encodes all the information that is already known, so to say. And this probability distribution will also enable the sampling of parameter space, something I'll explain in a couple of slides. Once you have the prior information, the next would be to compute the likelihood function. The likelihood function is essentially quantifies how likely the model represents the data. So in a sense, you need some sort of an estimate whether the model is close to data or not. And one simple case is some sort of a least square estimate. You take the model, which is A is a model parameter. You take f of A, and J denotes every single data point. So Fj minus Dj divided by sigma j. You scale it with the uncertainties in data. So this essentially means that whenever something is more uncertain, the denominator is larger, and it will have a smaller contribution to the misfit. So less preference is given to that, whereas a more precise measurement is given more weightage. So this is like a weighted least square sort of a thing. And this is what a likelihood function is. So if you consider this particular space, like here, I've just taken a function because the likelihood function is again just a function to demonstrate this. Suppose you have two parameters here, and in the two parameter model, you see all these local minima, right? And so these locations would be the parameter values which best fit your model, best fit your data. So
I have a question.
Go ahead.
What this f function is?
Can you be a little louder, please?
Yeah. What this f function is?
Oh, f is some model, like depending on your data. Suppose in our case, f would be the ellipse. Profile of the ellipse.
Ellipse, okay.
Yeah.
And A is a parameter that is a semi-major axis.
A would be each of these parameters. A would be A1, A2, A3, A4. That is all the model parameters.
And that sigma is coming from the original data?
The sigma is coming from the observed data, which is the error bars, essentially the error bars.
Okay.
So essentially, like you see, this data point has a larger error bar,
yes,
and
yes.
this data point has a very small error bar.
Yes.
So our fitting needs to take care of this such that more importance is given to fitting this data point over this data point.
Okay.
So when you scale it using the width of the error bar, then automatically when you sum over, this gets more preference over this.
Okay.
So this is typically done in the weighted least square fitting methodology. Is that clear?
Yes, thanks.
So yeah, so we have the prior information and we construct the likelihood function for a given model. So all we need to do is next, excuse me, compute the posterior probability distribution.
I have one more question.
Mm-hmm.
Where this exponential function is coming from for this likelihood function?
So typically what happens is because we are doing, this is a probabilistic analysis.
Yes.
The posterior is actually a probability distribution. So you need to construct a likelihood function such that this product of it is normalizable. You know, the integral is always one, so to say.
So okay, this is something like that we have learned in statistical mechanics, right? Particle function.
Yeah, it is. You can call it. It is similar to it. Okay. But this is essentially, you can think of it in parameter space as a Gaussian, sort of a Gaussian in local spaces. Like around this minima, wherever Faj is equal to Dj, you can approximate it to be a Gaussian.
Yes.
Okay, is that clear?
Yes.
Okay. So moving on. So how do we obtain the posterior probability distribution? Now, the likelihood function quantifies how likely the observed data corresponded to the given model. And using the knowledge of the prior, what we could do is generate a grid of model parameters, right? And what I mean to say is, here we can just consider R to vary from 0.05 to 0.75, the entire range. Take all possible combinations and then just explicitly compute the posterior probability distribution. But this becomes very, very inefficient as the number of parameters increases. For instance, we can do it with 1 or 2 parameters. You can just, it'll be a grid of numbers. So if you have, say, 2 parameters, which is R1 and R2, and you generate a grid with 10 different R1 and 10 different R2. So you would have to evaluate 100 different models and, to compute the posterior probability distribution. The moment you go to 3, the 100 becomes 1,000, and 4, it becomes 10,000. So it just keeps growing, exponential growth sort of a thing. Not exponential, it's a log growth. So it becomes inefficient if you have more than 4 or 5 parameters. So what you need to do is to generally be able to explore these highly general and efficient approach, and that is the Markov chain Monte Carlo approach. Here what we do is we construct Markov chains, which is essentially performing random walks in parameter space. So suppose you start off with in a 2-dimensional parameter space. Okay, so this is, say, R1, R2. And, you have some set of priors. Let's say you're trying to restrict your search space within this. And you start off this and you do a random walk, which is for the first iteration, you compute what the likelihood function is, you compute the posterior probability for that. And then you do a random walk, you move in some random direction, right? And then depending on whether the likelihood function there is better than the likelihood function here, it increases or decreases, you accept or reject the step based on some probability. So what happens is, suppose if this is like the global minimum, your random walk is sort of biased to move towards this region rather than moving in some random regions. So what happens is, once when you continue running the iterations for a large number of steps, you would end up, all the Markov chain walkers end up concentrating in the region around the minimum. And the advantage is, suppose we have multiple minima, not just one. Even in the case of multiple minima, suppose there is one minima here, one minima here. Some Markov chain walkers might end up getting sampling this region. Some Markov chain walkers might end up sampling this region. So effectively, within the region parameter space accessible by the priors, you would essentially be sampling the entire region, like exploring all the possible minima sites. And this is not the case if you're trying to do some sort of a least square fitting, where you just try to look for a minima. Suppose you do a gradient descent. Suppose you start from here, it will do a gradient descent and you'll end up with a solution here. And once you're at a minima, you'll have to use different techniques to come out of a minima and look for another minima and so on and so forth. Whereas this sort of a Monte Carlo analysis would give you, in a single step, would give you the entire parameter space or the portion of the parameter space which you want to access. Let me clear this. Yeah. So, so more likely models will have a higher acceptance probability, and less likely models have a higher rejection probability. And the biased random walk results in walker sampling the posterior probability distribution. And the advantage of this is this scales well, irrespective of the dimensionality of parameter space. So now let's just look at a small demo where what I've done is, before we start, in case someone wants to use this, these are the commands. You can just install the MCee using the Conda install command, and it's available on the Conda 4 channel. And you also need this the package called carlo, which you'll have to install using pip. This is for plotting and post-processing data. So what I do here is I generate some sort of a synthetic data where I'm trying to replicate what is actually observed, which is the location of the stars over a period of time with its own error bars. And what I do is, to generate the synthetic data, I give some true parameters. So the R1 and R2, which is the semi-major and semi-minor axis, have this particular value 5.34 and maybe let's say 3.14. Okay, and the Cx and Cy, which is like the center, would be at these two coordinates. So our, if at all our estimation is right, then we should get the values close to this, because this is synthetically generated data. So I get that, and I have a function which computes the log likelihood. And the prior, what I'm using is a flat prior, which is saying that I have no information about this. And all I'm saying is Cx lies between -6 and 6, which is somewhere in this half. I want to explore all the possible regions within that. Cy lies between 0 and 8, which is this and this, which is, so essentially it is almost this entire region. And R1 and R2 have can take values between 1 and 7, which is quite a wide range of values. So I define the prior, the likelihood function, and the log probability. So another ease of doing this is, because we are dealing with exponentials and Gaussians, we can just take the log probability and do a sum of these probabilities instead of doing a product. So, prior plus likelihood function would be the probability of the posterior. So what I do here is then, I set off the random walks, and let's see what happens if I give like 50 iterations of walking. As you can see here, the random walk starts off at different locations of Cx, Cy, R1, and R2. But eventually you see all of them converging. And this is not converged yet. So let me increase the number of parameters here, number of iterations, sorry. This will run for a while. And what we would like to see is, you see all of these starting out with various different initial conditions are eventually converging to a single point. In this case, it's a single point because the model is pretty simple. It's just an ellipse, and there is sort of a unique solution. There are not multiple solutions. But depending on the complexity of your model, this can result in branching out to 2 different points, 3 different points, and so on and so on. And we can also obtain the probability distribution and the estimation of it. And I have marked in blue the true values that I put in by hand to construct the synthetic data. And what I've estimated from by doing the MCMC analysis, the histograms are shown here. And because this is a probability distribution, it's one second. And because this is a probability distribution, you won't get a single value for an answer, but rather a distribution, which is, so to say, a value with an error bar. And we see that, it's very close to whatever we are getting. This is the supposed true values, these dots, and all the peaks are very close to the true values. And if I plot it, you see, this is the data, and these are the many models, which nicely fits the data. And I've shown the focus, the location of the focus is in the point, which is what we set out to do. And just to print out the actual error bars that I've gotten from this, CX instead of 959, I'm getting 943, 4.29, 4.31, 5.34, 5.33. So all of these are very, very close. So this is because I've also artificially injected some noise into the problem, and the noise could be very large, and which is why it's resulting in not the exact population. So if I reduce the noise a bit, synthetically reduce the noise a bit, let's say, if I reduce the noise, then you should see the inference to be much more closer to the previous inference. You see, it's gotten thinner, and I'll show it to you here. Yeah, this is much tighter. .297, 294. Now it's in the 3rd decimal place. So this is just so to say that it's so simple that you just construct this particular model, and you're able to fit the data and get the estimates very easily. So this is done using the Python package called MCee, which I would encourage everyone to go and check, because this is a tool. It supports parallelization, and especially if you're running things on the cluster, it's very easy. And yeah, that's it. We have actually found the locus of the point just by doing a parameter estimation. So just to summarize, so the Bayesian MCMC provides a very general and powerful method for parameter estimation. And it's especially useful if the likelihood function is multimodal. That is, if there are multiple minimum points, if there are degeneracies in the model that you want like to understand. And I had a small demonstration through which you're now familiar with the Python package MCee. There are 2 things that I would like to caution you about. One is the model needs to be computationally inexpensive. So as I showed you here, this required for such a simple model, I can say that this would converge in about 200, reasonable convergence, but maybe slightly more, 400 steps to actually converge. And that is possible, that you are able to evaluate the model 400 times not 400 times, 400 of these iterations for each of these MCMC walkers, and there are 32 such walkers, independent random walkers. It's able to do it because the model evaluation is so quick. So one of the main criteria for trying to apply this method is you need to have a very inexpensive model. So you would, a lot of models can be made optimized to a certain extent. So you would probably spend quite a bit of time trying to optimize the model so that you can do this. And because the sampling is done thousands, if not millions of times. And one more important thing is the inference is very sensitive to the choice of prior. So you need to be careful, or you need to have at least a strong justification for what prior that you're choosing. Suppose I choose a prior and the solution lies outside that particular prior, then you would not really get anything out of this particular simulation. You'll be wasting your time just running, computing different models, and it's trying to search for a solution, and you're not getting it. So when in doubt, when you don't know anything, it's best to use a flat prior, which is an unbiased estimator with a really wide span, so that explore a large parameter space. So that's it. I'm very interested to apply this optimization methods to different problems. So, if anyone wants to discuss or collaborate, please drop by 8270. I'd be very happy to talk to you. Thank you. Any questions?
Thanks, Samarth. Great talk.
Yeah, thanks.
I have a question, Samarth.
Yeah.
First of all, very great talk.
Thanks.
Thank you. My question is, in the model problem that you solved, the ellipse one, you used a flat prior, right?
Yes.
So, assuming you had taken a Gaussian prior, let's say, where would it come into?
So what I would, so a flat prior. So I'll tell you what the MCMC is actually doing. So it is drawing samples using this particular distribution that it
The initial position of the walkers is.
Oh no, initial position of walkers is completely independent.
Okay.
So that is just randomly generated. That is not dependent on the prior. Okay. What is happening is after you start off at, say here I've set you see there's a random number here. So this is just initializing step. Okay. So I'm starting at 32 different locations and it randomly starts there. What the flat prior or the Gaussian prior would do is where to go next. So to go next, it needs to, it's a vector, 4-dimensional vector with Cx, Cy, R1 and R2. So what is the probability distribution that it has to draw from, to move in a new random direction. So a random is not always just random, right? A random comes with a probability distribution for each variable. So that's what happens. So if suppose you have already some other observation which you are trying to improve or which you are trying to see the compatibility of it, you can use that observation. Say it's already known that what is that? Cy is 4 plus or minus 0.5, and you think you have a new set of data which is quite precise and you want to improve on it. So you can just say, okay, the Cy is not actually a flat prior. The Cy is a Gaussian with center at 4 and width of 0.5. And you can continue this.
Okay. So that means the direction of the movement of walker would depend on the prior, right?
Yes.
Okay. Thanks.
Yeah. Any other questions?
Yeah, hello.
Yeah.
Yeah.
I can't hear you, Snehalata.
Can you hear me now?
Yeah. There's a lot of echo.
Yeah, actually, I'm talking from Prasant's this account. I had a problem.
Yeah.
I was asking question on that random walk where you were talking about several minima. If there is a several minima, so
Yeah.
can you explain more about that, like how you address that part?
So it is addressed just by the random walk itself. Let me.
Okay, so finally it
So-
reaches a particular.
So suppose, these are, say, you're starting off with a wide enough search region, right?
Yeah.
And suppose you have one minima at 0 and one minima at minus 1.5. So some of these walkers would converge around 0, and some of these walkers would converge around 1.5. So, and because you're starting, your initial condition is you're distributing the initial conditions over the entire parameter space. You ensure that it's not concentrated around one. If you do end up, however, starting with a narrow search space, it's possible that you would not explore the entire parameter space. So you have to make sure that the initialization is wide enough. If you throw a wide enough net, that you catch everything else. That's what it is.
And if there are any degeneracy in the parameters, how will it handle?
Yeah, that degeneracy is a problem because say there has to be a way for you to
Okay,
regularize
so
it a bit.
Some prior like information that it should be within this range.
Yeah, so the prior should help to break the degeneracy. If not, you should probably regularize a bit so that one is preferred over the other or something like that.
Okay, fine.
Yeah.
Thank you.
Yeah. Thanks. Any other questions?
degeneration में issue होता है. देख
ठीक से काम नहीं करते मेरा ये वाला. अच्छा चीज मुझे लगता है बहुत टफ है.
easy है ना.
नहीं बताया कैसे.
Suppose I am running an experiment model and I don't know where the chain will finally converge a priori.
Yeah.
Then is there any way to find that and stop the code there?
Oh, that's why this requires a bit of trial and error. You try to run on a smaller set of parameters and get a reasonable idea of how. That's a good question actually. That is one of the problems because you don't know a priori. One thing is you could do is try to see analytically what kind of misfit function it is your model is, or so to say. Suppose you play around with the model a bit and you know that okay, some of these parameters reasonably fit the data well. Okay, and then you probably generate a small grid of parameters and see what the misfit function looks like there, or the likelihood function.
Okay.
If it's a very steep likelihood function, then you can expect that the chains converge relatively quickly, because a steep likelihood would imply that a higher weight is given to a random walk in the direction of the minimum. But if it's not very steep, then yeah, you would probably have to run for a longer number of iterations. But
Okay.
always try to restrict the number of parameters. Try, say here there are 4 parameters. Maybe fix 3 of them. Keep one variable and try playing around with it, because the lesser number of parameters, the faster the computation is, and so on. So you should be able to. It's a bit tricky that you have to try it out. There's no other way around it. There's no there's no fixed set of rules that if at all this is a problem, this needs to be the number of iterations.
Okay, thanks.
Yeah. Any other questions?
Shatanik has put up hand. You can ask your question.
Yeah. So in many cases in astrophysics, we often have to calculate what angle something subtends with respect to the line of sight, right?
Yes, yes.
So
yes.
in that cases, like if we run such simulations,
Yes.
the values, let's say for example, theta and pi minus theta, both are possible solutions.
Yeah.
And also like if you add 2 pi to each of them,
Yeah.
all of them will be possible solutions. So
Yes.
some of them will, some iterations will converge to theta, some will converge to pi minus theta.
So that's why I
how to
said, right?
resolve
Like
that?
whenever there's a degeneracy, you can always restrict. For instance, you know that there is a 2 pi repetition. So the search space, you can always restrict it to 0 to 2 pi. And second, you know, theta and pi minus theta. So maybe you can just look for 0 to pi, search for 0 to pi. Say that, you know, if at all a solution exists at between 0 to pi, there's also a solution between pi and 2 pi, right? So that way you can sort of break the degeneracy. You are manually sort of breaking the degeneracy. And that's what I was trying to tell Snehalata also. In case of degeneracy, if possible, try to remove it from the model itself. If not possible, then try to see if there is a prior, if at all there is a previously known data which favors one solution over the other, or yeah, I'll just go ahead with it.
And also as you have demonstrated in this case, all the errors are symmetric, right?
Yeah.
So are there cases where we can also obtain
yeah,
asymmetric?
definitely. Yeah, that completely depends on the problem and your model. So the errors can be not just symmetric, it can have any kind of a probability distribution. It's just a coincidence that this model gave us nice Gaussians for all the cases, so it's symmetric, but that's not necessarily the case. It can be a fat tail distribution. It can be. Any other questions?
I don't see any hands. You can...
Okay, let's give it a minute more and then we can call it a day.
Okay. Okay, probably no more questions.
Okay, yeah, so yeah, maybe you can just drop by 8270 if you have more questions, or if you need help installing this or using this, I'd be very happy to help.
Yeah, sure. Thank you,
thanks,
Samarth.
thanks.
Thanks again. I will stop the
sure.
recording.